Hi, everyone. Okay, so we have several materials today. So first we finish up the chapter 1, then we do a review on how to use R. Maybe we spent maybe I don't know 10 minutes, 20 minutes. Then after that we go to chapter 2. Okay, so at first chapter 1. So this is an overview of the textbook. So chapter 1 and chapter 2 are kind of an introduction to data science. So this chapter just briefly discuss the ideas of the data science, and the chapter 2 still we have some ideas, more general ideas about statistics, not really computer implementation or data analysis, but I discuss more ideas. There's several of the key ideas, such as the bias variance trade-off. Sometimes the very detailed statistical model that does not work well because the estimating such a model is too difficult with the small data set or something like that. And also we discuss the ideas such as the training and test error. So if we fit the model and it can explain the training set very well, but if we have new observations, sometimes it does not work better enough. So we discuss that kind of materials. And also we discuss the categorical variables and quantitative variables. So yeah. And chapter 3 is linear regression. And if you have taken either 50/30 or other statistics courses such as the Stat 5800 or maybe courses in other departments such as public health, then probably you have studied linear regression, but we have a review and maybe slightly more materials on linear regression. Then classification. The classification has not been discussed in Stat 50/30 or 5800. So we discussed logistic regression. That has been discussed in chapter, the Stat 50/30 in the last chapter that if you have taken my course. And the LDA, linear discriminant analysis, quadratic discriminant analysis, and the KNN, these are new methods. So these can be applied for classification problem with more than 2 categories. So the idea is if we have maybe 2 predictors, then we have 3 groups. Simplest criterion to distinguish these 3 groups is to use maybe a straight line to distinguish the 2 groups. So this is kind of linear discriminant analysis, the quadratic curve, and KNN, the nearest neighborhood. Sorry, the nearest neighborhood. What KNN stands for? Nearest neighborhood nose, maybe. So that is more non-parametric methods. So that we discuss the for each point, what's the adjacent points. For example, this point, this and this is the closest point. So this point, if the label is not clear, then this is most likely in the same group as these crosses. So this is the nearest neighborhood method. So we have some new models. And chapter 5, the resampling methods. We study the cross-validation and the some sampling and so on. The cross-validation is important method to evaluate how accurate your model is for new data set. So this is also, I think this is also a new chapter. This is not covered in the Stat 50/30 or 5800. And chapter 6, the linear model selection and regularization. Yeah, so the model selection has been done in Stat 5030. Probably you have studied AIC, right? So do you remember AIC? Model selection method. But the model selection method sometimes does not work. Suppose that we have 1,000 predictors, but we only have 50 observations. Then usual model selection methods does not work. Usually the 50 predictors are enough to explain 50 observations. I mean, the 50 predictors with 50 independent predictors that we can make a perfect model to explain the response variable. So we cannot improve anymore. So in such a case, we use so-called regularization method. So that we basically penalize the size of the parameter. So if we have y is equal to beta naught plus beta 1x plus beta 2x, so x1, maybe x1 plus beta 2x2 plus and so on, then we penalize if beta 1 is large or beta 2 is large. So in that case, actually, even we have more parameters than number of observations, still we can determine the optimal model. So this is a very typical case in some data set. So think about the doctors, diagnosing maybe the images of cancer patients. So images, even low quality images such as 100 dot by 100 dot images, if that is grayscale image, that is 100 by 100. So basically we have so each image consists of the 10,000 variables. So each variables means each dot, and each dot has the grayscale from maybe 0 to 64 or something. So in such a case, we have 10,000 variables. 10,000 variables for each image, right? But it's common that we only have 50 images. Maybe with out of 50, maybe 20 are from cancer patients and 30 are benign patients, right? So in such a case, doctors judge those images with those 50 images to judge which patients are, have cancer. And suddenly doctor learn after they see 50 patients, right? So in such a case, 10,000 variables, 10,000 predictors with 50, sample size 50. So still the such model is necessary in real world. So we study the shrinkage method and the regularization methods, and also the dimension reduction method here. And chapter 7 is beyond linearity. So relationship between x and y is not always linear, even though linear model is the most basic model in statistical analysis. So the one extension is linear to polynomial regression, but also that we have new methods such as spline or local regression or GAMs, generalized additive models. So we discuss in chapter 7. So these are also new materials. Chapter 8, the tree-based methods. So tree means that we separate cases. Often to make some decision that we separate cases, right? For example, yeah, so I don't know, for example, to judge if a person is overweight or something. Okay, so maybe BMI is one measure, but maybe the male and the female have the different weight, even if the heights are the same. So in such a case, at first we split the entire data set to female and male. Okay, and also even within male, we have several different groups. Maybe if the people are less than 15 years old, maybe they are lighter than adults or something like that. So we split cases. Then for each group that we may fit a regression model, then it can be more accurate model. So that is tree-based methods. And support vector machines, the support vector machines is the nonlinear model. So yeah, we will explain later, but we expand the space of predictors. So if we have predictor x1 and x2, then we only have the two predictors, then we need only two-dimensional space. But to identify very complicated pattern, sometimes it's beneficial to map all observations into higher dimensional space. Then it's easier to explain the model. Maybe we will cover it later. And chapter 10, the last year, we didn't cover this. So neural network and the deep learning. So deep learning is okay, so at first, the neural network is a kind of logistic regression with two layers. So basically, if we have X and Y, the predictor and response, maybe we have the intermediate product Z. We explain Z by X, then we explain Y by Z. So in that case, the model is more flexible. So that is the neural network, and the deep learning is that layer. We have more layers. Neural network also have several layers, not necessarily the 2 layers, but the deep learning have like the 10 layers or 100 layers. So in that case, suppose we have the very high dimensional space for X. Suppose we have 10,000 variables for X. Then gradually we reduce the information. That is very natural idea. Then we continue. And then we have finally a better model. So that is the neural network and the deep learning. And these are, the chapter 5 is general methods, but mostly chapter 3 to chapter 10 are supervised learning. And chapter 12 is unsupervised learning, principal component analysis and k-mean clustering. So this is 4-dimension reduction, and this is the clustering, basically classification with no labels. Yeah, and I focus more on ideas rather than computer implementation. Often this kind of courses, the ideas are missing, and just do calculation and done. But then you cannot get any ideas. And idea is timeless. So it's the most important thing to learn, especially in college environment. Okay, so these are this is an overview of the textbook, and certainly we skip to chapter 11, 13, and so on. I think it's a little bit a stretch to cover all chapters of the textbook in one semester. I think the computer science department or data science program, they spend 2 semesters to cover this textbook. And okay, so how to use R? So R and Rstudio is used in this class, and I'm using computer to explain this. So yeah, but at first I want to mention that the R is available on the comprehensive R archive network. So if you'd like to install for the first time, then you go to you just type the CRAN in the Google, then you can go to this website to download. So installation is even easier than Microsoft Office. This is the free software, so open source software, so it's easier to install. And Rstudio is also easy to install, except for making the PDF files. So yeah, you can go to the https www.rstudio.com. So this is this software is developed by a company, so for-profit company, but the free version is very popular, and I think if you pay some fee, maybe you have more convenient features, but I don't know many people who bought the version with a fee. Okay. Yeah, so these are the chapter 1. Do you have any comments, questions? So far? Oh, do you have any quizzes, questions on quizzes or troubles on quizzes? Okay. So have you heard of these methods? For example, tree-based methods, like the boosting, bagging, random forests. You haven't?
Yeah, I've heard of a fair
Okay.
number of these.
Okay, where did you hear these names or concepts?
I guess random podcasts. I don't know. Also, I think maybe last class you mentioned some stuff too sometimes.
Possibly,
here
yeah.
and on about, yeah.
Yeah, I see. Probably neural network that you have heard of it, right? Maybe many of you.
Yeah.
Neural network. So neural network is mathematical algorithm. So maybe neural network has two meanings. One is, really the network in the brain, and the other is the neural network as a mathematical structure. And those are connected. I think not really. So it has some similarities, but probably not that close. Okay, so now we want to use my computer. So I was using iPad, but and R cannot be run on iPad, unfortunately. Actually, there is a version, the iOS version, but it's not useful, unfortunately. Yeah, and R console, yeah, maybe I quit this first. Yeah, so this is the R language. So after you installed it and you click the icon, then this window appears. So I'm using a Mac. Oh, sorry. I think I have to share my screen. Yeah, maybe. Yeah. Okay, so this is the window for R. So this just works as a computer. 1 + 1 = 2. I just type 1 + 1. So you don't really have to compile anything, and you can just get the output. So it's similar to Python or Gauss or MATLAB. And the convenient feature in R is that we can deal with matrices and vectors. For example, the vector, if you want to define vectors, then you can define like this. So this is a vector which has the 4 elements. So 1, 4, 6, and 7. So if you want to take summation, then you can just type the SUM, or mean, you can do like this, and the standard deviation. Also, it have functions to generate random numbers. For example, if you want to generate the 50 random numbers, which follows normal distribution, you can just type the R norm of 50. Maybe once again, then these are random numbers, so that these are different. Okay, so the first one, the first run, the first one is -0.195, second one -1.76, but the second run, the first random number is 1.57, second one -0.23. So it's different. If you want to replicate the same output, you can set seed. So set seed of random numbers. So, sorry, we have to put some numbers, some integer, 1, 2, 3. And if you put some integer, then our norm of 5. Okay, so we have, sorry, R norm. So you get 5 numbers, and if you set theta again, and the type R norm 5, then we get the same numbers. And even on your computer, that you got the same number, negative 0.56. So once I asked students to submit a homework to generate random numbers after setting a specific seed, and the students use different OS and operating systems and different versions of R, and always get the same answer. Yeah, so the quiz question about how to use R like this. And R has some functionality to create graphs, for example, histogram of 100 random numbers. This, yeah, so different window appears. I think in Windows versions of R, that there is a larger window here, and within the large window, we have the R console, and also the window to, the window nested by the larger window to show graphs. The Windows version is slightly more convenient because, for example, we can save this graph by, for example, file, the save as. And for Mac, I think we can only save this as PDF. But in Windows, you can choose other formats. And in Mac, if you want to save this as JPEG or the other bitmap or something else, then you have to write some code, short code to save this graph as, in a different format. Yeah, and also it can deal with matrices. So, for example, A is a matrix with maybe all elements 0, and we have, for example, the maybe 2 rows and the 3 columns. Then A is this, and you can modify this matrix as this. So the one element of A, the first row, first column is of A. We assign the 123 to this. Then A becomes this. So matrix calculation, for example, if we have the B as this matrix, then you can multiply B by A, and that can be done by this. It's a little bit annoying to type these 3 symbols to make just a matrix calculation. A transpose A is T of A. This is relatively simple, and A inverse is solve of A. So A is not a square matrix, so we cannot take the inverse. Okay, so solve B, then this is the B inverse. Yeah, so basic operation can be done this way, and we have the several functions. You can see the chapter 1, 2 of the Stat 5030 slides discuss how to use R. Yeah, logarithm is natural logarithm. So log of 10 is equal to the 2.3, not 1. Yeah, exponential function is exp. You can see any other things. And yeah, we have already assigned some things. So yeah, so you can define x as 2. You can also define in this way x equals 2. And y is equal to 3. Then x plus y is this. So you can x times y, or x to the y's power, and so on. Yeah, so you can access the we have defined vector as yeah, anyway, so x is Also, we can make a sequence, such as sequence from 5 to 10. So this is a vector with 6 elements, 5, 6, 7, 8, 9, 10. You can do x plus 1, for example, in this way. Basically, all calculations are component-wise, except for matrix calculation, such as, matrix product, like this. You can access specific element of x in this way. So this is the second to third element, or you can say second element and fifth element. Yeah. So most major functions are so variance of x, standard deviation of x, or simply the length of x. We have 6 elements, so 6. We can repeat, for example, 1, 2, 3 several times, then 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is a vector with 11 elements. So this is how R works. Yeah, maybe some other numbers, other functions. Maybe the useful function, maybe sort function. For example, okay, so we define this as x, then we sort x, then this becomes 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. And reverse of sort of x, then, oh, sorry, reverse. Then the 3, 3, 3, 3 first. So in this way, then we can do many things. And maybe, okay, so we define the new vector, maybe randomly like this. Then we can have the rank function, rank of A. So this returns 5 numbers. So this means the 5 is the second smallest number, 3 is the first smallest number, 7 is the third smallest number, 10 is the fifth smallest number, and 9 is the fourth. So using this, you can use this function to manipulate some vector. Order of A, 2, 1, 3, 5, 4. Okay, sorry. I think this A is really a bad example. Maybe we put some numbers. No, rank of A, sorry. Okay, A and rank of A. Order of A. Rank and order. Sorry, maybe I use different example. Not sort, rank of A and order of A. Okay, so now we got the different ones. So rank, this means this is the fifth smallest observation, and this is the third smallest observation, and so on. What is order? Order means the fourth observation is smallest, and the third observation is second smallest, and the second observation is third smallest, and the fifth observation is fourth smallest, and so on. So order function can be used to order the vector. So sort A makes this vector, but also so if you pick the fourth element of A, that is 2, and the third element of A, that is 9, then second element, the 11, fifth element, 12, right? So if we type A of order A, so this is the same. Order of A is this vector. So then that we can sort A. So this can be useful that if we want to sort, matrices by some order. Maybe some data frame. So yeah, so suppose that we have X. X is as okay, so maybe A is this, so that we define B. So B as, for example, 1, 1, maybe 1, 10, 100, 1,000, 10,000 or something. Then sorry, the C. We have to put C to declare vector. And if you want to combine these two columns, then we can define this data frame. So suppose we want to sort this data frame by A, then we can type D order A. Sorry. Then that we get the the order, the rows of this so-called data frame by A. So 2, 9, 11, 12, 20. So, and the B is also ordered at the same time. So 2 comes with 1000, and 2 comes with 1000, and 9 comes with 100, and so on. So in this way, order function can be useful. Yeah, so you can do, yeah, so maybe some other useful variables such as range. To make a scatter plot, sometimes you have to specify the minimum possible value to maximum possible value. So this is useful, the range function. And yeah, also you can use the minimum function, a maximum function. Yeah, maximum A, yep. And so on. The correlation also can be calculated, and B. And the plot function can make a scatter plot. So A and B. So this number is too large. So maybe it's more meaningful. Yes, one is this. Maybe we have some negative correlation, right? So correlation of A and the log of B, and this is -612. Yeah, sometimes we have more complicated function. This is correlation test to see if this correlation is significantly different from 0. And the correlation test function, then we get the p-values of 0.27. So this is larger than 0.05. So correlation is not significantly different from 0. Yeah, so yeah, in this way the R works. So it's similar to Python. So probably we don't have much. You don't have much trouble if you have used one of the matrix languages. Yeah, so I think that these are the most basic things for R. Yeah, maybe also there are several classes. So the A was a numeric vector, but also we can define. Yeah, by the way, the R is the case sensitive. So the A, capital A and lowercase a are different. And you can also define the character vector such as this. For example, the female, male, female, male, female. Then C is a character vector. So for example, we can check if C is equal to female. Then you can see the first, third, and the fifth are true. So double equal, it's condition. So we check if C is equal to female element wise. Yeah, so yeah, maybe it's the most annoying part of R is the class. So the C is now character, but also as factor C, then this becomes a factor vector. Maybe I would say the C.F. This is a factor vector. So factor, so the character vector, the R does not recognize the inside. So the R inside the quotation. So R does not recognize the first, third, and the fifth are the same, the same categories. But when we make it as a factor vector, then the R recognizes that there are two levels, the female and the male, and the first, third, and the fifth observations are female, and the second and fourth are male. And also as numeric. you can see that R recognize only two categories. If we make the C.F as numeric, the 1 to 1 to 1. 1 is female and the 2 is male. As numeric C, we cannot really judge this because the C is the character vector, so R does not recognize the how many categories and which observations are the same. So it makes an error. Okay, so now this numeric, maybe Cn, what happens if we make it as a character vector? It returns to female, male, female, male, female. And logically, it cannot happen. So R already discarded the information that this is FEMALE. So if we make this as character, just this becomes 1 to 1 to 1. So changing from character to factor, factor to character. So this is very tricky. So maybe I don't know, the significant percentage of errors come from the complication. And also it's useful to learn the list in R. So we have several items, the matrix or vector or number, but also the list. List includes multiple objects. Sorry, maybe before that, we want to distinguish matrix and the data frame. So matrix, we can define matrix A, maybe, sorry, matrix, maybe M, matrix M as the matrix, maybe. So this is the matrix from 1 to 6 by column, and 3 rows and 2 columns. So this is M. And also that we have data frame. So data frame, for example, we have A here and the C here, and we can make the data frame of AC. And M and D are kind of similar in the sense that we have the rows and the columns, but these are slightly different. Because for M, everything is numeric, but the D, actually A is the numeric vector, but the C is a character vector. So we have different things. So data frame can have different objects in this, the one spreadsheet, but the matrix, they should have the same property for each element. So everything should be numbers or everything should be characters. So everything should be the same. So we combine 1 to 3 to 4 to 6. Then we can this matrix, but we sorry, I cannot say that. So this the M and D look similar, but they are recognized in a totally different way. M is a matrix and a D is a set of 2 vectors, and the first object is A and the second object is C. A is numeric vector and the C is C is a character vector. So M is originally a matrix, so you can make it as matrix, but if we have D, then if we transform D as a matrix, then it becomes slightly different. You can see that we have quotation. So that means that so in R, the matrix, they should have the same property for each cell, each element. So since the female and the male are characters, so 20 and 11 and 9, 2 and 12, these become characters too. So R does not recognize this as 20, just the letter sequence of the 2-0. Yeah, so list is several list consists of several objects. For example, we can define the instructor as cars and the time as maybe the start time and end time of the lecture. So for example, maybe R bind, we combine rows of the two numbers. Okay, then, okay, so we can define the list. Yeah, we can declare the list by, I think, list. And we have to have the name. So maybe ins as the instructor and the time, maybe like time. Okay. This is actually, it should be equal. Then this list consists of two objects. The first object is instructor and the second object is lecture time. If you wanna extract this one, 1846, then you can at first type this. So second object, then 22. Then we can extract this. You can also change this as, okay, so we extend the lecture to 7 p.m. Then list becomes this. So actually the data frame is a special case of list. So list consists of multiple objects and the data frame actually consists of A and C. So the first vector and the second vector. So actually the data frame is a special case of list, but it looks like a matrix. Yeah, so this is probably the most important part in R. Yeah. And maybe after that, maybe the session management may be important. So you wanna, at least you wanna import some data set, right? So we have some data set somewhere. For example, oh, do you have any questions so far? Especially for those who haven't used R before. Okay. And how to import data set? That is maybe the next one. And the maybe, okay, so suppose we wanna read this data set. This is the Facebook's stock price in the past 10 years, past 9 years, maybe. And if you wanna read this CSV file, then at first you have to, specify the path. So get WD gives the default directory of R. Then if you wanna read the sum file from this page, then you can specify you can set directly. So this is actually this path. So users, the Kazuhiko Shinki, WSU teach the stat 503020F and quiz. So if you want to change the directory, then you have to type the set WD, and this is the same, but you can add the WSU and teach and the stat 503020F and quiz. Then you set working directly. I think we need the quotation maybe. Then, okay, so we have no errors, so that we specified this. So then if you want to read this, then you can, for example, define D as the read.the table of Facebook and the CSV, and this has some header. So the header is equal to true. Then separation symbol, this is CSV file, so the comma separated. So then we get the data set D. Yeah, So you can see, for example, the first several rows of the head D and so on. Yes, I think these are the basic concepts of R. And the next Rstudio. So anyone has not succeeded to create the Rstudio, I mean PDF from Rstudio? No. Okay, so Rstudio is this. So if you open Rstudio, and this sample file is available on the website. Yep. So Rstudio consists of 4 windows. So this is basically the text editor. And this is R session. So you can type, for example, 1 + 1, then it returns 2. And also that you can select the some lines in the text editor, then you can put run, then you can run this code. But also that you can compile this file. So this file consists of some sentences such as this, and also some explanation. Explanation like this. I use the LaTeX format to write some sentences. So 3/2, there I typed the backslash, the frac, FRAC, the 3/2. And if you want to make a PDF file from this, then you can type the init, then it takes some time, but it runs, then finally there you get some PDF file like this. So I would like to submit your homework in this format. So some title, your name, then this. So the convenient thing in Rstudio is that it automatically run all of your code, and you put just side by side. So it stacks the output, the code and output. So for each line, the result is here. And also, if you make a histogram in your code, then the histogram is also put here. And also you can write some sentences such as this. Yep. And if you make a really, for example, the scatter plot with many observations, then it becomes heavy. So I suggest to transform it into JPEG file. So you can see that in your code, here. So when you start the R code, if you specify the device is JPEG, and you specify the number of dots per inch, then you can reduce the size of the file. If you only have 100 observations, that's fine. But if you have 10,000 observations, the JPEG file is much lighter than the PDF file or the PostScript file. Yeah, but this init function, basically there's several necessary executing files there. So if you have installed LaTeX first, probably that you don't have much trouble, but sometimes you have trouble to init the file. Yeah, in Canvas, we have this source code in Rstudio. Yeah, source code and the PDF file. So I put both files in Canvas. So yeah, you can try to compile this. Okay, and maybe the last thing to cover from R is the linear regression. Linear regression, maybe open high. Yeah, maybe I can use the Facebook dataset. So I have the Facebook dataset. So I type the structure of D. So we have the 2092 observations of the 7 variables. And this is the open the price at open and the price at close. So open and close, these are, of course, the similar numbers. So open and close. So maybe we consider to fit the closed price by open price. So what's the correlation? Okay, maybe at first maybe attach this data set so that I can use the open without specifying the the name of the data set, and open and close. And if I plot the close price, the price at open as X and the price at close at Y, then we can make this scatter plot. So this, of course, for each day, the open and the close have similar prices. So the very high correlation. And maybe I can fit the close on open. It's pretty good linear model. So almost the intercept is 0, maybe slightly negative, and the coefficient of the coefficient. So the close, okay, so suppose the close is alpha plus beta times open, then beta is 1.00084. So coefficient is almost 1. And if you want to see the summary of this, maybe it's convenient to name this as LM1. Then summary, then you can get more detailed the explanation. So estimate, but also the standard error of estimate. Say this is beta hat, then this is standard error of beta hat. So this is the ratio of the this over this, and this is p-value when we test if this is equal to 0. So you can see that intercept is not significantly different from 0 because p-value is more than 0.05, and open, this coefficient is highly significantly different from 0. You can see. And maybe residual plot, we can check. There are several ways. The diagram. Yeah, so residual plot, maybe residual of LM1, and we plot this against open price, then you can get this. So yeah, it's not random. So yeah, certainly the open price is higher than residual is higher. So larger number, if the numbers are larger, then the change is larger in absolute value. So we can get this kind of thing. Yeah. Yeah, and other functions that you can learn from your slides. So probably you got some good image on how to use R. Yep. Do you have any questions on how to use R, or even you have taken 50-30, maybe you forgot several functionalities? I think it, yeah. Okay, so maybe we start chapter 2. Do you have any questions, comments? What other courses are you taking this semester? Anyone is taking 5800?
Yes, me.
Oh, okay. Who is the instructor?
I can't actually pronounce his name, but something. Sorry.
The 58 okay. Instructor, maybe Fatih, no?
Yes.
Okay.
I don't know his name though.
Yeah, he likes to teach that course. Yeah. I haven't. Yeah, I'm a statistician, and I haven't taught that course for about 10 years. That's more mathematical course, and that's very important course if you are studying statistics.
Mm-hmm.
Okay, so now the chapter 2. This is chapter 1. So chapter 2. So chapter 2 is the statistical learning. So typical question in data science is this. So objective that we want to increase sales of a particular product. And the data, we have data set. Sales, advertising budgets for TV and radio and the newspaper for 200 markets. So this is a pretty large data set. So each line comes from one market. So that is probably compiled by some survey or something. And maybe companies record, maybe. And action, which advertisement budget should we increase, the TV, radio, or newspaper? So data science, usually that we consider the business, implication. So not just analyze data, but we need some action. So that is the idea of the data science. So yeah. And this is the profile of the data. So sales is on the y-axis, and x-axis are TV and radio and newspaper. And note that the X scale is different. Maybe if we use the same scale, maybe it's slightly easier to interpret, but you can see TV advertisement. Actually, in many markets, the companies spend more on TV rather than radio or newspaper. So, and the red one is regression line. I don't know, they did some transformation before making this trend line or not. But anyway, so this is trend line in some sense. And certainly all trend lines have positive slope. But do you find any other findings from these 3 scatter plots? For example, what do you see when you compare advertisement on TV and advertisement on newspaper? Or TV versus radio, yeah.
TV is the best, I guess.
In
Make
what
more
sense?
sales. Well,
right. Okay, I see.
It generates the most sales or whatever, right?
Right, but note that the x-axis are different, right? So TV, we have the 0 to 250 here, and the sales goes up by maybe goes up by 13. Sales goes up by 13 when TV advertisement increase from 0 to 250. But the newspaper 0 to 100, then it increases by 5. So probably it's similar amount, right? The slope is actually similar probably. The newspaper X increases by 100 and Y increases by maybe 5, right? Here, 0 to 250, 2.5 times larger, then maybe slope is the same, right?
Yeah.
Sales is 13 larger, yeah.
Like, yeah, the scaling on the x-axis throws it off a little bit.
Yeah, and but if we adjust the scale, which is better, TV or newspaper? Suppose that the TV, why?
Because the observations are closer to the line.
Yeah. So that's the point, right? So the newspaper, we are not really sure if this is significant or just made by this point or this point, right? So we have more randomness, but here we have more consistent pattern. So maybe TV advertisement maybe better in the sense that this slope is more robust. Yeah, that's great. And radio and the TV, But the radio, okay, so the trend is less clear compared to TV, but the slope is much larger probably, because the radio, the advertisement amount increase from 0 to 50, then sales increases by maybe 11. Only 50, then 11. Here, 250, then only 13 or something. So radio, it's a little bit risky, but in terms of expectation, it increases sales most efficiently. I mean, most efficiently. Yeah. Or we can say that if we have a lot of money, then suddenly TV is good. Just to spend a lot of money on TV, then maybe it's good. Yeah. So there are several findings here. And at first, we discussed what kind of models we can consider. The first thing that we can come up with is just linear model. Y is a linear function of x1, x2, x3. But in general, that we have this model. Maybe we have interaction between x1 and x2, such as, the y is equal to for example, maybe beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. But sometimes maybe, if the people see some advertisement on both TV and the newspaper, you think that that is reliable company, and the sales goes up even more. So beta 4 here, or something like that. Or I don't know, if you see TV commercial every day, it isn't much different from the seeing commercial once every 2 days. So in such a case, maybe we have nonlinear effects, such as y is equal to maybe beta naught plus beta 1 x1 square root or something like that. So there are many possibilities. So in general, we can think about this model, or you can separate cases and discuss. Or yeah, there are several ways. Yep. And but here anyway, so this f is unknown, and the even simpler model that these numbers are unknown. So we have to estimate these numbers, or estimate this function. So estimate is denoted by f hat. So f hat is not the true f, but the something close to f. So I say the Pizza Hut may not provide the true pizza, but it provides something similar to the true pizza. So Pizza Hut or f hat. So it's similar, but not the truth. Yeah, and in traditional statistics, we assume the x is deterministic. So x does not have randomness, and y has randomness. In some advanced modeling, also x have some randomness. But certainly, the x have some errors. Yeah. So if you think about the relationship between height and weight, then of course the relationship have some variability, but also measurement have some variability. So sometimes the measurement has also variability, I mean randomness. But for simplicity, mostly in this course we assume, I think that all of the materials assume that x is deterministic. Only the epsilon and y are random. Yeah, so the forecasting means this. Okay, so the truth is y is equal to f of x1, x2, x3 plus epsilon. But when we estimate f, then this is our best guess for y. And we have several objectives in a data science problem. So one is forecasting. So we estimate y hat. But also some questions arise about inference, and sometimes that we want to estimate the beta I itself. beta I itself is of your interest. So either some variable has positive effects or negative effects on y. For example, I don't know, use of the marijuana has positive impact on the mental disease or negative impact on the mental disease. It's not clear, and whether it's positive or negative is important. And in this context, how much the sales increases. So radio has probably the largest coefficient. But also another topic is test if beta I is really not equal to 0. So for example, the newspaper advertisement, the effects, the size of the effect, the beta I is almost the same as TV, but it's less clear if the BI is significantly different from 0. So test is also another question in data science. Do you have any comments or questions on this? Yeah, so now we see how accurate your model is. So you may fit the multiple linear regression model or a simple linear regression model or a more complicated model. Okay, so suppose you set up a model, you estimate the model, how accurate this is. And the most popular measure for the error size is this mean square error. So take summation of squared errors, then divide by the sample size. So why take square? So the first reason is that we want to ignore sign. So if yi is equal to, suppose, the 10.4, and think about yi hat is equal to 10.9 or yi hat is equal to 9.5, so 9.9. Okay, so both have the error of 0.5. We put the equal penalty on these two errors. So that is one idea. And also, the sum of squares is very natural quantity, right? So maybe, I don't know, Euclidean distance, x1, y1. Okay, so then x2, y2. Then what's the distance? So this distance is x1 minus x2 square plus y1 minus y2 square, and finally take square root. But essentially, the sum of squares represents the distance, maybe squared distance. So this basically this summation explains the distance between the truth and our estimate. So it's pretty natural to take summation of the squared residuals. Divide by n, this is pretty natural because we have n observations, so we standardize by n. Yeah, so MSE is the sample version of the expected size of squared error. So, the expected value of this and this are different, but it's similar quantity. Right, so if we have observations, think about the very basic statistics. So we have observations x1 to xn, then the summation of xi, I is equal to 1 to n, then divide by n. Okay, so this is x bar. And x bar is not equal to expectation of x, but this is similar quantities to expectation of x. Kind of realization of expected squared error. Okay, so I think that this is probably, that's fine. And this one is a new material. It does not appear in Stat 5030. Reducible and irreducible errors. So at first, assume that errors are IID, so observations are independent. And consider that this model. So xn, yn are given for n is equal to 1 to n. And then we have new observation xy. Okay, so we have a kind of the training data with size capital N, and we have a new observation xy. And what's the expected error size? Expected squared error size. Okay, so this is to be accurate. Maybe we put bracket here. Okay, so that is the equal to this. Okay, so because the y is the fx plus epsilon, this is our assumption, right? And y hat is the f hat of x. This is just a different notation, but the same thing. Then what should I do? So we wanna okay, so when we make a prediction model, that cannot be perfect, right? So suppose that we, that entirely identify the true relationship between sales and advertisement, but still that we have some error. For example, maybe weather changes, then sales changes, or maybe the business goes down. I mean, the business condition, overall business condition in the entire economy goes down, then sales goes down. So we cannot explain that part. So we have some irreducible errors and also the reducible errors, that is the model accuracy. So we want to basically single out this irreducible error. And how to do that? And we have epsilon, so we separate the epsilon and the other parts. So, okay, so we take just epsilon and other parts. So epsilon here, and we want to separate this. So fx minus f hat of x plus epsilon. So we separate epsilon and the other term. Then, okay, so we have fx minus f hat x square, then epsilon square, and the interaction term, right? So just it's the same as the x plus y square in the junior high school. Okay, we have this, right? So now the x is f of x minus f hat of x, and the y is the epsilon, and we have the cross term xy here. And but actually the second term, so this one is 0. Why? Because the epsilon is, okay, so y is equal to f of x plus epsilon, and this is new observation, right? So this is new observation. And this f hat, f of x is deterministic, and f hat of x, so this determines by x1 to xn. x1, y1 to xn, yn. Right? So these are different observations. So originally we have n observations and we have new observation. So new observation and old observations are not related. So it's independent. So expectation is separated. So this is expectation of epsilon times expectation of f minus f hat. But the expectation of epsilon is 0. So error has the mean 0. That is always true as long as mean exists. So this term disappears. So finally, that we can get this is equal to this one and this one. Okay, so variance of epsilon square is irreducible error. We cannot make it smaller by improving the model. But certainly, if f hat is more accurate, then the first one goes to 0. So this is the reducible error. Of course, if sample size is limited, this cannot be 0. But if we improve the model and we have more sample size, then we have a larger sample size, then it becomes converges to 0, hopefully. So we have reducible and irreducible error. Yeah, we have one quiz question from this. Yeah, so again, so this is the reducible error and this is irreducible error. So in real world problems, irreducible errors exist because y is partly determined by factors not included in X. For example, the sales may also be influenced by temperature, business cycle, rival companies' products, etc. Yeah. So, okay, so now the 6:45, so we finish here. Yeah, but before that, I would like to mention one thing. So this one, okay, so basically we want to minimize the error size, so expected error size, and this is approximated by mean square error. Okay, so yeah, so we have y value and the y hat value, then we calculate the MSE. So basically the MSE can be decomposed into irreducible error and the reducible error. In reality, we cannot calculate this exactly, but approximately this left-hand side is approximated by MSE. Yeah, so that's it for today. And yeah, next time we continue chapter 2. Do you have any questions? If you don't have, see you next Tuesday, and I will upload the quizzes tonight.
Thank you.
Thank you.
Have a good night.
Have a good night.
Yeah.
Have a very good weekend.
Bye, everyone.
Professor.
Bye. Bye.
Bye.
Bye. Thank you.
Oh, see you then.